In this second video, we're going to look at theoretical probability, and that's looking at the frequency of an event. Frequency is determined by a study of all the possible outcomes. So computing theoretical probability, again, we're determining the probability of an event. But in theoretical probability, you're looking at number of times your event would happen over the number of possible outcomes, or you could think of that as the number of objects in your sample space. Possible outcomes. So in our dice example, our die example earlier, we were finding the probability of odd, and we could do an experiment where we roll a die 30 times and see write down the list of each roll that we get and then count how many odd ones there are to get the empirical and experimental probability. But if we think about it, on a die, the sample space is 1, 2, 3, 4, 5, 6. That's the total sample space. And there are 3 odd numbers. So my probability, theoretical probability, that I get an odd would be 3 out of 6, which is equal to 1/2 when we simplify. So we're going to look at a couple of examples where we use theoretical probability. So in this example, we have each individual letter of the word Tennessee, which I lived in Tennessee once for a while, 4 years. Each of the letters of the word Tennessee is placed on a piece of paper, and all 9 pieces of paper are placed in a hat. We're going to identify the sample space. The sample space S is going to be each of those letters. T with repeats, because each letter goes on a sheet of paper. Oh, that should be an E. I lived there. I should know. Okay, so we're going to find the theoretical probability if one letter is selected at random from a hat. Okay, so the number of possible outcomes is 9. Okay, but we're going to look at the probability of S being selected. We count how many S's there are. There are 2. So our probability of an S would be 2/9. The probability of not S would be 1 minus 2/9, or essentially how many other letters are there? 1 minus 2/9 is equal to 7/9. You could think of 1 and rewrite 1 as 9/9. Let me erase that so you can see it. So you could write 1 as 9/9, which is 100% happening, minus the 2/9 for S. And we get that not S would be 7/9 is our probability. A consonant is any letter that is not a vowel. Our vowels are A, E, I, O, and U. So a consonant in here would be, we have, I'll circle in yellow, T, N, N, S, S. So there are 1, 2, 3, 4, 5. So that would give us 5/9 for probability of a consonant. Probability of T or E. Okay, T or E means we count it if it's a T and we count it if it's an E. So 1, 2, 3, 4, 5. So that's going to be 5/9. Probability of a W, well, there are no W's. There will be no sheet of paper that has a W on it, so the probability of that happening is 0. And probability of not V, well, they're all not V. So the probability of that is 9 out of 9, which equals 1. Okay, so this is just an example we could see where we use some theoretical probability. We're going to look at compound probabilities, and one thing that will help us determine the compound probabilities is if we can model each scenario with a Venn diagram. So again, everything's tying back to what we did in that first unit. In example 8, we have a single die is rolled 1 time. Model each scenario with a Venn diagram and compute each compound probability. So in this first scenario, we're saying we're looking for the number is odd. So my first number is odd is my first circle on my Venn diagram. My second circle B is the number is greater than 4. And then remember, we have the universal set. So anything that does not fit into one of those circles would be in the universal set U, which is any number on the die that does not end up being odd or greater than 4 or both. So let's go one at a time. On a die, our sample space, I'll write up top, is S equals 1, 2, 3, 4, 5, and 6. So let's go through each number. 1 is odd, so it would go here. 2 is not odd, and it is not greater than 4, so 2 would be in the universal set. 3 is odd, so it would come in here. 4 is not odd, and it's not greater than 4, so it would go in the universal set. 5 is odd, and it is also greater than 4, so it goes in the both range. And then we have the number 6, which is not odd, but it is greater than 4, so it goes in that red circle. So now we can use this to help figure out these probabilities. Now remember, if we have an or, that's our union. And if we have an and, that is our intersection. So remember, intersection, I'm going to shade that in light gray, would be the overlap between the two sets. The union would be everything within here. Then we also have the complements. We could also look at those as well. So we're going to look at the probability of getting an odd roll or greater than 4. So it's counting or, that's this one right here, the union. That's all these in between both circles. So contained in any of the circles, green or red, we count it. So the probability of that happening, how many values are in those circles? Well, we count 1, 2, 3, 4 out of 6. That simplifies down to 2/3. Okay, now let's think about what's the probability of it being odd and greater than 4. That's the intersection. That's my and that's the space in between both. So how many numbers are in both circles? That is the number 5, and so it shows up one time out of the 6 possible numbers. So these are theoretical probabilities that are compound probabilities for this situation. So now we're going to do B, and I don't really have a lot of space, so let me see if I can duplicate the page, but then do the work for B above. For this example, the two possible things that we're looking for is that A, the number is even, so this circle will represent the even numbers. B is the number is less than or equal to 4, so we have the number is less than or equal to 4. So then we're going to, again, draw our universal set on the outside, and if it doesn't fit in to even or less than or equal to 4, then it goes in the universal set. And again, our sample space for a die is 1, 2, 3, 4, 5, 6. Okay, so we're going to go through each one. 1 is not even, but it is less than or equal to 4, so it would go in the red circle only. 2 is even and it is less than or equal to 4, so it goes in the both area. 3 is odd, so it's not even, but it is less than or equal to 4, so it goes in the red circle only. 4 is even, but it is also less than or equal to 4 since it's equal to 4, so that goes there. 5 is not even, and it's not less than or equal to 4, so it goes in our universal set. But 6 is even, so it would go in the green circle. Now, I hope you notice that these probabilities right here don't match my Venn diagrams, so I have the wrong example. That's okay. We're going to cross that out. We're going to make up some. So we're going to say, what's the probability that we have an even number and the number is less than or equal to 4? So the and is the intersection. That's the overlap between both circles. And we have 2 out of 6 because there are two numbers in that middle region. So 2 out of 6 is the same thing as 1/3. Okay, now let's think about the probability that we have not even or less than or equal to 4. And I'm going to kind of put those in parentheses as well. So not even or less than or equal to 4. So that means essentially that's the complement of these two circles. So in that case, how many numbers are in the complement of the two circles? So what's in the universal set that's not in those two circles? Well, that's just the number 5. So there's only one value out of the 6 values on the die, 6 possible outcomes. So we can make up more probabilities. We could say, what's the probability of that the number that we roll is even or is less than or equal to 4, and that would be 1, 2, 3, 4, 5 out of 6. So it would be 5, 6. We can make up several possibilities like that. So let's take a second. We might not answer this with respect to those examples, but we might want to look at what it means for two things to be mutually exclusive. That just means that they can't happen at the same time. So if I were to flip a coin, I can't get both a heads and a tails at the exact same time. Okay? It's not possible. If I pull a card, one card out of a deck, I can't get both a king and a queen if it's one card. Now, there are things that are not mutually exclusive. So like if I say a number less than 4 and even, a number could be both of those things. So anytime you have a situation where both couldn't happen at the same time, we treat that as being mutually exclusive, but you can have situations that are not mutually exclusive. So then we can also look at what it means for there to be odds. So the odds in favor of an event are the number of successes it's the ratio of the number of successes to the number of failures. So let's say I have a jewelry box and I have 5 pearls, 2 emeralds. Let's say we're looking at necklaces or something, and 7 diamonds. Also, I don't have jewelry, but that's besides the point. Anyway, let's say I was looking at the odds of me getting a pearl. So if I were to go into that jewelry box, eyes closed, and pick something, and let's say they all felt exactly the same way, which we know that they don't, but let's say they were all perfectly round, spherical items, and I could touch them, and they all felt the same, and I picked one at random. My odds would be the number of successes to the number of failures. So a success, in that case, if I was looking for a pearl, would be 5, and my failures would be the sum of everything else. So 7 plus 2 is 9. Now I wrote it in the colon ratio form. You could also write it as a fraction, 5 to 9. Now if I was looking at the odds against my event, that's going to be the opposite, the number of failures to the number of successes. So in this case, with my pearls versus everything else, the failures sum together to be 9. And then with the colon form, we'd say 9 to 5. So I would have 9 to 5 odds against me selecting a pearl. I can write that as a fraction. Notice that that fraction is larger than 1 because the odds are not looking at your total possibility of like randomly selecting a pearl. It's just saying what are the odds compared to what's happening in the total situation. So odds are treated separately or slightly differently than probability. So please keep that in mind when we're talking about the odds of something happening versus the probability, because they can get convoluted. And you can think of like, what are the odds of getting a heads if I flip a coin? Well, the odds of me getting a head is 1, but the odds of me not getting a head is 1. So the odds are actually 1 to 1, but the probability would be 1/2. Let's look at this example and see kind of the difference. We have in a class of 30 students, 18 are liberal arts majors. If a student is selected at random, determine the probability that the student is majoring in liberal arts. So the probability of a liberal arts major, which we're going to abbreviate LAM. So we're told that there are 18 liberal arts majors, and we're told that there's a class of 30 students total. So theoretically speaking, or I guess this could be experimentally, because if we ask 30 students, and 18 of them are liberal arts majors, that's experimental. We have 18 out of 30, which simplifies down to, divide each by, 6? We get 3/5. Okay. The probability of the students not majoring in liberal arts, there's two ways you could figure that out. We could take 30 minus the 18, and that equals 12. So the probability of not liberal arts majors, and that little tilde in front of it represents a not, or you could put LAM complement, same difference. That's going to be 12 out of 30. You could also have done 1 minus 3/5 to get your answer, but we'll write it 12/30. And when I simplify that down, divide both top and bottom, let's divide by 6 again. That's the largest thing that can go into both of them. We end up getting 2/5. Now notice 3/5 plus 2/5 would equal 1, which is the entirety of the class, right? They're either liberal arts majors or they're not liberal arts majors. Let's look at the odds. The odds against the student majoring in liberal arts, well, that's going to be how many are, the odds against would be failures to successes. So that's going to be 12 to 18, or we could write it 12/18, which is the same thing as 2/3. And then for D, what's the odds in favor? So that's successes to failures. So that's going to be 18 to 12, which would be 3/2, or 18/12, and then that simplifies down to 3/2. So make sure you're treating probability and odds differently, okay? Because the way we find them is different. This example puts us into an interesting perspective. We have 3 kind of sub-examples within this. First one is, if the odds in favor of Lady Q winning a horse race are 1 to 4, then the odds against Lady Q winning the race are, and that's going to be the opposite ratio. So this one was successes to failures. So odds against are going to be failures to successes. That's going to be 4 to 1. Okay. If the probability that an event will occur is 2 out of 3, or 2/3, then the odds in favor of the event occurring are, this is tricky. You have to think about what's happening. It's saying that the probability of the event is equal to 2 out of 3. That means 2 favorable outcomes out of a possibility of 3 outcomes. So that means, let's say we had 3 slips of paper that were labeled 1, 2, and 3, and our event that we were looking for was, we're looking for a number less than 3. So there are 2 possibilities that would give us a success, and then there's 1 possibility that would not give us a success. So the odds in this situation, which I've kind of just made an example to represent this, would be the probability of getting a number less than 3 would be 2 out of 3, or 2/3. But the odds in favor of the event occurring would be 2 to 1, and the odds against would be 1 to 2. Okay, so think about how to use probability to determine odds. And then we're going to do the vice versa. So if the odds against an event are 1 to 3, so that means 1 failure and 3 successes. So how much do we have total? Total, we have 4. The probability that the event will fail to occur, so that's our failures, is 1/4. And the probability that the event will occur would be the successes out of the total. That would be 3/4. So we can use the odds to find the probability, and we can use the probability to find the odds. Whew. There are a few more examples in the guided notes, but I feel like this has kind of covered pretty much everything that you might need to see. A few things to remember, and this is just for homework purposes or for common knowledge purposes, also for possible test question purposes. You do need to know things about a deck of cards. So one thing to know is that the total number of cards in a deck is 52. There are 4 suits. That's going to be your hearts, your diamonds, your clubs, and your spades. Each suit has 13 cards. Those cards go from ace and then 2 through 10. And then we have a jack, queen, king. And my family played games all the time, so I know this is kind of, this might be redundant if you played a lot of games growing up or card games, but if you don't really play a lot of card games, this might be a good refresher. And I'm trying to think. And there are 4 types of each of these cards because there's one in each suit. Okay, so 4 suits, 13 cards per suit. Okay, and that's helpful because you could be asked to find the probability of finding or drawing a 4 out of a deck of cards. Well, there are 4 fours. There's the 4 of hearts, the 4 of diamonds, the 4 of clubs, and the 4 of spades. So my desired outcomes or my desired event occurrences is going to be 4. And the number of times that that occurs is 4 out of a total number of 52 possibilities. And that simplifies down to 1/13. Okay, so please, please, please make sure you know your card facts, know your dice facts. Well, with a coin, I hope it's not too difficult with heads and tails. But hopefully you can see that this is useful information that might help you. And you might want to do your own little experiment. You might want to take a coin and flip it 10 times and see how many times you get heads and how many times you get tails. Does it match theoretical probability? If theoretical probability says if I flip a coin 10 times, I should have 5 heads and 5 tails. But we might see if we try that experiment ourselves that that's not necessarily the case. So this concludes our second video on probability. I hope that you found it helpful, and if you need any help, please let me know. Send me an email and I will get back to you. Thanks.